Section: Introduction. In this section, we explore the significant role of deep neural networks, which have shown remarkable success in various fields like image classification, natural language processing, and even playing chess. Recently, large language models have emerged as a prominent technology, but as these models grow larger, their training costs become extremely high. This drives us to investigate their training dynamics to reduce the cost of acquiring intelligence. We propose that viewing these models as circuits can offer valuable insights into this process. Circuits in our context refer to pathways within a neural network that transform inputs into outputs. Inspired by the human brain, artificial neural networks function like complex circuits of interconnected neurons, where information flow is managed by rectifiers. The term circuit has gained traction in mechanistic interpretability, which seeks to understand and improve the reliability of neural networks. We can think of a neural network as a combination of circuits, which can also be broken down into smaller subcircuits. Identifying these circuits can be subjective, as we aim to capture meaningful units of computation, such as algorithmic circuits or memorization pathways. By conceptualizing neural networks in terms of circuits, we gain new perspectives on how they operate and process information. Our main focus is to analyze how these circuits evolve during the training of neural networks. To study the dynamics of circuits during training, we concentrate on a straightforward task, the sparse modular addition problem. Here, our inputs are sequences of tokens in a specific mathematical structure, and the targets are the sums of the first few terms. We define our input sequences in a way that allows us to work with different vocabulary sizes and sequence lengths. Our contributions in this paper revolve around using the circuit concept to shed light on how neural networks learn and enhance their performance. We clarify what circuits are and how they help us understand the training behavior of neural networks, noting that gradient descent strengthens useful circuits while eliminating less useful ones. We also discuss how gradient descent encourages the development of subcircuits, which assist in tackling complex tasks by breaking them down into manageable steps. Additionally, we address the challenges of identifying circuits and how strategies like curriculum learning and data curation can facilitate the discovery of beneficial subcircuits. Overall, our work offers a fresh perspective on the training dynamics of neural networks and highlights the advantages of thinking in terms of circuits for improving their performance. While the concept of circuit dynamics applies to various neural network architectures, we specifically focus on the transformer architecture due to its proven effectiveness. We examine a one-layer transformer with cross-attention. Our model processes an input sequence by first mapping each token to a multidimensional embedding, then adding a positional embedding based on the token's position. This is followed by a normalization step. Next, we compute the attention mechanism using query and value matrices, which allows us to derive a new representation of the input sequence. We skip the key transformation to simplify the process. After this, we apply a feed-forward block consisting of a two-layer multi-layer perceptron with a specific activation function, followed by a residual connection. Finally, we map the output back to the vocabulary space to produce a probability distribution for predicting the target from the input sequence. Throughout our experiments, we train the model using gradient descent with a specific optimizer and set parameters for learning rate and embedding dimensions. Section Summary. In this section, we introduce the concept of circuits in neural networks, emphasizing their role in understanding training dynamics and performance optimization. We outline our contributions, including how gradient descent reinforces useful circuits and the importance of curriculum learning in discovering effective subcircuits, while also detailing our focus on the transformer architecture for empirical success. Section: Is learning about pruning circuits? In this section, we explore how gradient descent can help us develop useful circuits while eliminating the less effective ones. We also introduce visual tools to better understand this pruning process in attention modules. To grasp the impact of updates, we visualize an attention layer as a bipartite graph, where nodes represent both input and output sequences, and the edges are weighted based on attention scores. The thicker the edge, the stronger the attention. We illustrate attention for sequences with repeated entries. Throughout training, we track attention maps over iterations, marking decreased weights in blue and increased weights in red. Initially, we notice that gradient updates can sometimes strengthen attention on irrelevant tokens. This is evident in the first few profiles, where certain tokens, despite not contributing to the output, are reinforced. However, updates generally push attention towards the relevant tokens, particularly the first 5. Our visualization aids in understanding gradient descent better. Each step updates network weights based on their local impact on the output, meaning multiple circuits can be reinforced by a single update. To illustrate, if we input 2 identical sequences, the update will strengthen both circuits leading to the output, potentially creating duplicates due to the localized nature of updates. As we continue iterating through the data, we observe how gradient descent reinforces both spurious and relevant features. The spurious features, which do not contribute to the output, show fluctuating attention weights, while the relevant features become more dominant and eventually prune the spurious ones. We believe this behavior is typical of gradient descent in neural networks. As we process pairs of inputs and outputs, the circuits that consistently predict the correct output become more prominent, leading to the pruning of less effective circuits. When we analyze the circuits learned for a specific task, we find that the network first computes an intermediate result before arriving at the final output. This is evident in our visualizations, where attention focuses on the number of zeros among relevant tokens. As we train the model on different data, we see it organizing sequences into clusters based on specific criteria. This structure becomes more refined with further training, indicating that the network effectively breaks down tasks into smaller, manageable subtasks. This approach is similar to how convolutional neural networks extract features in layers, starting from basic textures and moving to more complex patterns. The emergence of subcircuits is expected, as the information processed at each layer builds on the subcircuits from previous layers, and gradient descent reinforces those that contribute to accurate predictions. Section Summary. In this section, we explore how gradient descent can enhance useful circuits while pruning non-essential ones, using visualizations of attention layers to illustrate this process. We observe that as training progresses, spurious features are gradually diminished, allowing circuits that consistently aid in accurate predictions to dominate, akin to how convolutional neural networks extract hierarchical features. Section: Easing Optimization Paths. In this section, we explore the insights from the previous discussion and their significance. By formalizing our ideas mathematically, we can derive valuable theorems and improve optimization methods. We present an experiment in a controlled environment that demonstrates how well-structured curriculum learning can help us tackle a challenging problem, similar to finding a needle in a haystack. When addressing the modular addition problem with specific parameters, we aim to create a circuit that can generalize from a limited training set to a much larger testing set. Our findings indicate that training from scratch often results in networks that simply memorize the training data without being able to generalize to new data. However, by initially training the network with simpler parity data, we enable the first attention layer to perform addition modulo a certain value. This pre-training allows us to initialize the network with a useful subcircuit, making it easier for gradient descent to find a circuit that generalizes well to the larger dataset. In practice, we first train the network on data with a specific value for 3,000 epochs, then switch to a different value and continue training for an additional 7,000 epochs. This process creates a noticeable gap in performance, as illustrated in our figures. We observe a significant barrier between the memorization approach and the generalization achieved through curriculum learning. The high loss associated with the model trained from scratch explains its inability to escape local minima and find a more general solution. Our observations in this controlled setting have broader implications. For complex problems, identifying the right circuits can be challenging and often requires extensive data. High-capacity networks may resort to memorizing training data without generalizing. However, there are often simpler solutions based on sub-circuits that can be learned through proxy tasks. Curriculum learning can facilitate the acquisition of these modular components, which can then be applied to more complex tasks. This highlights the practical benefits of curriculum learning and the importance of careful data selection to foster effective circuit learning.